Today's is a criterion for picking what to work on, and it runs against your instinct. It comes from Google's chief scientist. Here's what he told a room full of founders.
His words, look for something where the model succeeds 0% or 1% of the time, not 20%.
Before you move on, sit with that for a second. Why would 20% be the bad number? Common sense says 20% means the path works and you just have to finish it. Isn't that exactly when you charge in? His answer is that 20% is the most dangerous place to stand. This episode takes that criterion apart, along with the caution he added himself, the half almost nobody carries, and without it, this whole thing is just candy. First, who's talking and where? This matters. The speaker is Jeff Dean, chief scientist at Google. He's also one of the people behind the origin of Google's own chip, the TPU. We'll get back to that. The venue is Y Combinator's startup school, this year's. The host is YC's Diana Hu. About 6,000 people in the room, that number comes from the host herself, when she asked him a question. Let me put the venue on the table.
This is an event run by a startup incubator for 6,000 founders.
An incubator's own conference has a built-in position. You still have a shot. And the person saying it works at a big lab. Put differently, he's telling people how to survive inside his own company's blind spots. I'm not throwing out the content over that. The opposite, the criterion is specific, and he added a caution to it on the spot. That's not a talking point. But you should know which chair this is coming from. All right, back to the criterion. One thing that's easy to skip, what the model can do is his second filter, not his first. What's the first one?
He says that's the number one selection criteria he tries to apply for what problem to work on next.
And that first filter is whether you actually want to get up and do this, and whether it's useful to the world, to a lot of people. His framing is that if you wake up not wanting to do it, or you're building something that isn't much use to anyone, you're behind before you start. I won't dwell on that one, because it sounds like something everyone says. The second one is where the information is.
He says, second, look at what the current more general models can do in that problem domain. He continues, if they're completely failing, that's probably a good sign. And if they're kind of able to do some of it, but not very well, that's maybe not a great sign.
Why? This is the pivot of the whole episode. Here's his reason.
He says that's probably a sign that the capability is starting to be present in those models. He continues, and with more training data, or larger scale models, or whatever, it's likely to get better.
Which gives you the line.
He says, look for something where the model succeeds 0% or 1% of the time, not 20%.
Let me put that in blunter terms. 0% is good news. 20% is bad news. Because 20% doesn't mean almost there. It means the next model will finish it on its way past. Everything you pour in there gets zeroed out by a version bump, not beaten by a competitor, flattened by an update. 0%, by contrast, means the thing isn't on that curve at all. It needs something else. The host pushed back with a good question. So how do you find those? Are they effectively out of distribution from the training set? He gave two paths. The first is data.
He says sometimes it's a product you build that has access to a particular kind of data the underlying model might not. His example, you're building something to help users organize all their own personal information, and the model won't necessarily have access to that. He says then you can have a big advantage, because all of a sudden your product has visibility into important data.
Notice the logic of that path. The model can't do it not because it's dumb, but because it can't see. And not being able to see doesn't fix itself when the model gets bigger. The second path is training something small and specific.
He says it could be some incredibly hard problem where, if you get the right training data, you can train a more specific model than a general purpose one, and do it very affordably. He says training a niche model for that particular problem may not take much compute, but you can get something highly accurate. He says that can be a really good building block for solving an important problem the general model doesn't handle well.
The host landed a nice one after that. You people are organizing the world's information, so that part is probably pretty well covered. That joke actually names what both paths have in common. They're both looking for the part the big labs aren't looking at. Which brings up the second chair, his own explanation for why that gap exists at all. He's blunt about this.
He says Google, the Gemini models, and their hardware infrastructure are all trying to build very general models that can do almost anything. He continues, but in a lot of cases, that means we don't have a lot of attention on particular domains.
And then the line everyone quotes.
He says that's where the 2 or 3 people in a room, building something they're really excited about, can have an advantage.
The 2 or 3 people in a room. Say that in front of 6,000 founders, and you can guess how it lands. But if this episode stopped here, I'd just be selling you a line that feels good. Because he hit the brakes on it himself immediately. This half is the other half of the criterion, and almost nobody carries it.
He says, but I would also caution that the general models are definitely getting better at a broader and broader range of things. He continues, so you have to figure out whether the thing you're working on is going to be a durable thing. He gives 3 markers. Will the models at the forefront get better at it in the next 6 months, or 12 months? Or is it something they won't be able to do for a couple years, or 3 years? He says you want to weigh that as you're deciding what to work on.
Put the 2 halves together, and the criterion is finally complete. The model can't do it today isn't enough. It also has to be something they can't catch up on within a year or 2. The first half alone, go find what models can't do, is a correct and useless sentence. With the second half, it turns into an uncomfortable exercise. You have to honestly estimate how long until the models reach you. And there's no answer key. What he gave are 3 time markers, not a formula. The third chair is another question he got. The host asked, what's one assumption the 6,000 people in this room hold that's already false about AI? Here's his answer.
He says people don't quite realize how possible it is to have agent-based systems that can run for a long time. He continues, not just an hour or 2 hours on a problem you care about. He says in some problem domains, with highly capable models underneath, you can get them to run for days or weeks and do really complicated tasks. He says some people are starting to see inklings of this, but he doesn't think everyone has internalized it, and it's going to be a pretty big deal.
The host followed up. What task have you actually run for weeks? What did you tell the agents to solve? His example is concrete.
He says you can tell agents to go implement completely new versions of software in a different programming language. He says those versions might have better safety properties or better performance, and the agents can go off and actually do it in a pretty serious way.
Put that next to the criterion from earlier, and you get an uncomfortable implication. If agents can run for weeks, the shelf life of the model can't do this is shorter than you think. Because a lot of things aren't beyond the model, it just didn't have the time, the context, or anywhere to keep what it figured out along the way. That last part is my read, not his. I put it next to his 6 months or 3 years to make one point. That estimate only gets harder to make. Now for the history. This next part was set up by the host, so let me get the attribution right first. She said it, not him.
The host says, one thing you're very well known for is that you're really good at napkin math. She continues, back in 2013, when speech recognition started to work at Google, you did the napkin math. If every Google user talked to their phone and used speech recognition for just 3 minutes a day, you'd have to double the server fleet. And instead, you basically built a custom chip, and that was the origin story of the TPU.
His response was yeah, and then he went into the details of what happened at the time. So those numbers are the host's, and he confirmed them. I'm attributing it that way. By the way, if you've heard me go through that table of latency numbers every programmer should know, that table also started as something he taught inside Google. But what I want out of this isn't memorize the orders of magnitude. It's what he did after the arithmetic came back. Normally, when the math says you'd have to double the fleet, the conclusion is that the feature is too expensive, ship it later, or cut it to half the users. His conclusion was, then don't use this kind of machine. 2013 was general hardware isn't enough, so build a specialized one. And the most interesting thing in this interview is that 13 years later, he ran the same move again. This time, it's him talking, not the host.
He says you're going to see more and more high-performance, low-energy inference hardware systems. He continues, because everyone is now realizing that inference is the key to making these agent-based systems available to more and more people, and that latency really matters. He says specialization of the hardware is a key way to make things more energy, efficient, and lower latency than more general-purpose computational devices, like, say, GPUs or TPUs.
Did you catch that last part? More specialized than GPUs or TPUs, and the TPU is the chip he built. 2013, general hardware isn't specialized enough. Build the TPU. 2026, the TPU isn't specialized enough either. Build something more specialized. Same move, twice, 13 years apart. And that's the same thinking as the criterion we opened with, used two different ways. The criterion says, look at what general capability reaches today, then decide whether to go in. The chip says, price out what general hardware would cost, then decide whether to switch tracks. Both times the move is the same. Run the numbers first, then decide. Not passion first, reasons after. He also threw out one more thing to imagine.
He says, imagine what you could do with something where the latency is 50 times better.
Let me get to what I actually think, and what I'm watching next. First, the way this criterion is easiest to misuse. Go find what models can't do gets heard as go find an obscure corner. But his caution says the opposite. Obscure or not doesn't matter. What matters is whether general capability swallows it within 6 or 12 months. Something obscure but easy may get done by the next model on its way past. Something popular but genuinely hard may still be yours in 3 years. So the criterion isn't telling you to hide. It's telling you to estimate. And I should be clear about its edge. What he gave are 3 time markers, not an algorithm. How to make that estimate, and how accurate it can be, he doesn't say. That part is empty, and this interview won't hand you an answer. So what am I watching? 1, the 20% zone. The things models can sort of do, but not, well, by his account, that's the batch the next generation collects first. That one is checkable. Count how many products sit right in that band today, then count again in 6 months. 2, the 3 time markers he gave. 6 months, 12 months, a couple of years, those are his, not mine. Which means they can be reconciled later. 3, the inference hardware line. Because if the person who built the TPU is saying the TPU isn't specialized enough, this round of specialization won't stay inside one company.